Hello everyone, this is Joe with Joe Talks, and in today's video we are going to take a look at the front suspension of a dirt late model. And in this video we are going to do a position analysis of that front suspension. So we're not going to get deep into camber, caster, toe, those types of things. There's plenty of videos out there on the internet, but what we are going to do is go through a calculation approach that will tell us the points on our front suspension in 3-dimension space. And so each one of those points we are going to use the Cartesian coordinate system, and we're going to get an X, a Y, and a Z position for each one of those points. So let's take a real quick look at what we're talking about here. So on a dirt late model, or really any short long arm front suspension is going to be laid out this way. We've got an upper control arm, a lower control arm, and then a spindle and a tie rod mechanism connecting the system to a rack and pinion or some other steering input. Now what we're going to do is we're going to calculate the point, the three-dimensional point of the lower ball joint, the three-dimensional point of the upper ball joint, the three-dimensional position of the outer tie rod joint, that spherical joint. And then we're also going to calculate 2 points on the spindle axis. So an inner spindle and an outer spindle point. So that can be any points but along the spindle axis. Or in other words, the axis that the wheel rotates around. Now one of the characteristics of our calculation approach is going to be that it will consist of 2 inputs. So the first input is going to be the heim-to-heim distance of the shock, or in other words, the shock length. And the second input is going to be the inner tie rod position, or in other words, the position of the inner tie rod spherical joint. And so you might say, well, why do we want to make this calculation set up to have those 2 inputs? Well, a lot of times when you go to do testing, like at a racetrack or something, you can use data acquisition to collect data on your race car. And so 2 of those data points that you can collect is the shock length and the steering input, or in other words, the steering rack position. And so with those 2 inputs and using this calculation approach, we can calculate the position of our front suspension based off of what those 2 endpoints can be. So at any point in our testing loop or in our testing data set, we can determine what the position of that front suspension is. And so using these calculation outputs, the points that I talked about earlier, we can then calculate the camber, the caster, the toe, kingpin, inclination angle, scrub radius, all of those other characteristics of a front suspension that you often find in tuning books and things of that nature. So if you've never heard of trilateration, it's a pretty simple process. It is an approach that you can use to find the position of an unknown point using the position of 3 known points and the distance from each of those points to the unknown point. And so when you talk about satellites, basically in that scenario, the unknown point is the person on the Earth, and the 3 known points would be the satellites out in outer space. And so at any point in time, you know the position of, say for example, 3 satellites. And I know in satellite applications it's a lot more complicated because there's a lot more satellites, but in a slimmed down version you would have 3 satellites with known positions and then a known distance to the unknown position on Earth. And so we are going to use that exact same application except on our front suspension. So let's take a real quick look at our model again. So here the unknown points would be the points that I talked about earlier, but in this situation we do have known points on the chassis, and those would be the pickup points on the chassis. So in our example, we're going to hold the chassis stationary, and then we're going to move the suspension components with the shock movement and the steering rack movement. So on our chassis, our known points would be on the upper control arm. We have the front upper control arm mounting point, we have the rear upper control arm mounting point. And then on the lower control arm, similarly, we have the front and the rear mounting points of the lower control arm. And then on the lower control arm, we also know where the shock is mounted relative to those front and rear lower control arm points. And then on the spindle, we know locally on the spindle the distance between the upper and lower ball joint. We know where the outer tie rod mounting point is on the spindle, and then we also know the spindle axis characteristics of the spindle. And so as we go about doing this, we have to measure all of these points. And I'm not going to go real deep into how you measure this stuff. That's another video in and of itself. But in short, we can measure those pickup points on the chassis relative to the chassis frame of reference. And then we can also measure the lower control arm. We can do a bench measurement where we can measure the points of that control arm and do the same thing for the top or for the upper control arm, and then we can also measure out the spindle. And so we would do all of that on a bench top in our shop, and we would measure each of those components in the component frame of reference. So for example, on the lower control arm, you might designate the rear mounting point as the origin point. You might put the front mounting point on, say, the x-axis, and then measure where the ball joint is and then where the shock mounts. And then you would have all of those pickup points on that local component in the component's frame of reference. So if you're not familiar with frames of reference, again, plenty of other videos on YouTube. You can go research that stuff or any engineering textbook. But the key is that we're measuring each of those components, the dimensions in its component frame of reference. And then using those points, we can back calculate the distance between the points using basic Pythagorean theorem. So again, if you're not familiar with Pythagorean theorem, go look it up. It's a pretty simple calculation. And so knowing the pickup points on the chassis and then the calculated distance within each of the components, we can use trilateration to solve for our unknown points. Now, before we get too deep into doing our position analysis, let's talk just a little bit about the trilateration calculation. So I'm not going to go too deep into how to do this calculation. There's some good resources out there. Specifically, there's a paper out on the internet, and I'll put the web link in the description below. But an individual from the University of Georgia did a paper, and it's called From Barns to Satellites. And so he goes in and talks about the different calculations on how this is done, specifically probably with satellites, but the same application is done here. And then there's also a Wikipedia example of a computer program to do this. And so when we set this up, you're going to have to write a function in whatever platform you're using. And so one of the benefits of using this GPS application is it's something that you could do in Excel, really. If you're not real savvy on computer programming, specifically I like to use Python, but if you don't know how to program in Python or any other applications, you can use Visual Basic or VBA in Excel. It's not overly complicated. But you will have to create this trilateration function in your software. And a couple of other things you'll have to create is a dot product function and I think a cross product function also. But those are not overly complicated. Those are all real basic three-dimensional mathematics applications. But anyway, I wanted to put up an example here of some of this code. So this on the screen now is the Wikipedia example, and up here at the very top I've got the website where you can go look at this. It's on GitHub. An individual has it. I think it's actually been removed off of the actual Wikipedia page, but this individual has it on Stack Flow, I think is what the site's called, but it's on GitHub. But anyway, you can walk through this and see how the actual calculation is done. Again, I'm not going to go too deep into this because the actual trilateral calculation probably is a good video in and of itself. But what I've done is I have modified that just to my own application in Python, and I'm using the Spider console in Python. And so here you can kind of see, and if you're welcome to pause the video if you just want to copy this in your own Python script. But this is the trilateration function that I am using. And again, feel free to pause and copy as you see fit. Now, one of the characteristics of the trilateration function is that it yields two results. So it uses the quadratic formula as part of its solution process. And obviously, if you remember back in high school algebra, the quadratic formula has a positive and a negative result. So one of the things we have to do is do an inspection to determine which one of those solutions is the logical solution, because one of those will be obviously not correct. It'll be clear out away from your car, for example. So there's only one solution that will be correct. So, but this trilateration function is something that we're going to call several times in our solution process. So again, you'll have to create this and use it, but once it's created, you just call it as a function in your program. So it's not complicated at all. So. Okay, so now that we've talked a little bit about the trilateration function, let's talk about how we can put that function to work for us and actually do our position analysis. So what I've got here is a function that I wrote, and it's called kinFront or kinematic function. And I put this in a function format because ultimately you may end up wanting to use this calculation system in a larger model, like if you were to do a full vehicle model. And so that's why I have this as a function format and not just a calculation. So, and one of the other things you'll notice here is we have to tell the function all of those points that we talked about earlier. And in this application, I kind of hard-coded those in, but in reality, you would more likely pass those in as a matrix of values. So, but right here is where I've input these values. Now let's take a real quick look at our solid model again. So over here, in this view, it's kind of hard to pick up the actual points that we're talking about. So I've kind of recreated this into a more simplified model where we can actually see the points that we're talking about. So here, for example, we've got the lower control arm. So the front lower control arm point, the rear, the upper lower control arm, front pickup point, the rear. We also have the inner tie rod mount that would be on the rack, which I obviously don't have drawn in here, the upper shock mount. So all of these points are hard, what we might consider hard pickup points on the chassis. And then out here on the lower control arm, we also have a point for the lower shock mount, and then all of the spindle points being the upper lower ball joint, the outer tie rod mount, and the inner and outer spindle axis. So what I've done here is if I were to go measure these component parts, I've entered each one of these pickup points, the X, the Y, and the Z component into this script that I've got here. So if we come over here and look, we'll see the, for example, the upper control arm point on our solid model was 55 and 318 thousandths. And so here you can see where I've got that entered in. And so I've just done that for all of the chassis components. And then here, for example, you can see where I've entered in the spindle components. And so these are all local to the spindle. So this is all in the spindle coordinate system. And we've taken these local coordinate systems and then back calculated using Pythagorean's theorem the actual lengths. So what we're looking for over here when we do these calculations is we're looking for the length from the lower control arm front mount to the lower shock mount. Same thing with the rear point to the lower shock mount, and then the distance from the shock to the lower ball joint. And we need those values for the lower control arm. And then for the upper control arm, we simply need the front mounting point to the ball joint, the rear mounting point to the ball joint. And then for the spindle, we simply need the ball joint, upper ball joint to the lower ball joint. And then we need from the lower ball joint to the outer tie rod, the upper ball joint to the outer tie rod. And then we'll also need the inner spindle to the outer tie rod, the outer spindle to the outer tie rod, the inner spindle to the upper ball joint, and the inner spindle to the lower ball joint, the outer spindle to the upper ball joint, and the outer spindle to the lower ball joint. And so all of those distances that I just described are distances that we can calculate using those points that we measured on our bench in our shop. So that's why we measure those points before we put our model together. And so one thing to point out here is the difference between vector quantities and scalar quantities. So not to go too deep here, but basically scalar quantities, which a simple length is considered a scalar quantity, that quantity holds true regardless of what frame of reference you are in. So if we measure a distance in the component frame of reference, which is what we just did using those component frame of reference points, that distance holds true, and we can transfer that directly into the chassis coordinate system. And what we are doing here is we're calculating all of these final points in the chassis coordinate system. But just to be clear, we're using the locally measured points in the component's frame of reference to calculate those scalar distances. Now that we have calculated all of the appropriate distances that we need for each of our components, we're going to start using that trilateration function to do our position analysis. So this is kind of a closed form solution, but I say kind of because it isn't really just one calculation. We're going to do a sequence of calculations to calculate our overall suspension position. And so there's actually 7 different sequences that we're going to go through. But each one of the sequences does the exact same thing. We just call the trilateration function. We just change the inputs that we use, that we put into that function. So the first sequence is going to be to calculate the position of the lower shock. So the upper shock is stationary because it is against the pickup point on the chassis, but as the shock moves, obviously the lower shock moves, and we need to identify that lower shock position. So one of the inputs to the trilateration function is the shock distance, but we also have the pickup points of the front and lower control arm. And now that we have done the calculations, we also know the distance from the front lower control arm to the lower shock. And we also know the distance from the rear lower control arm to the lower shock. So our first sequence, we will take those 3 known points, the upper shock and the front and rear lower shock, and those 3 known distances, and we will calculate the position of our 4th point. And in this case, it is the lower shock mount. And so that is what we are doing here in sequence 1. And so once we know the position of our lower shock mount, that lower shock mount then becomes an input into the next sequence of our calculations. And so the next sequence of our calculation is to find the position of the lower ball joint. And so we use the values that we calculated in our local frame of reference in our lower control arm. We now know the distance from our front lower control arm to the lower ball joint. We know the distance from the rear mounting point of the lower control arm to the lower ball joint, and we know the distance from the lower shock to the ball joint. And so we know the two pickup points of the lower control arm, and we now, from our previous sequence, from sequence 1, we know the position of the lower shock, and so now we can use all of those as inputs to our trilateration function to calculate the position of the lower ball joint. And so we go through that sequence, and the output of that is we now know the position of the lower ball joint. And so the third sequence is to find the position of the upper ball joint. And so again, we know the distance from the upper front control arm chassis mount to the upper ball joint. We know the distance from the rear upper control arm to the upper ball joint. We know the distance between the upper ball joint and the lower ball joint from our spindle calculations. And we now know the position of the lower ball joint. And so we use those as inputs again to our trilateration function. And then we calculate the position of the upper ball joint. And then we just keep going through these sequences. And so sequence number 4 is to find the position of the outer tie rod, right? So now we know the upper ball joint position. We know the lower ball joint position. We know the distance from the upper ball joint to the outer tie rod from our spindle measurements. We know the distance from the lower ball joint to the outer tie rod, again from our spindle calculation or measurements. We know the tie rod length, because that's just the measured length, the hard part of the suspension. And then we know the position of our inner tie rod mount, and that is actually an input. We know that from our data acquisition because we can measure that same way we measure our shock length for sequence 1. And so using all of those as inputs, we can now calculate the position of the outer tie rod. And so now that we know the position of the upper ball joint and the position of the lower ball joint and the position of the outer tie rod, now we simply need to calculate the position of the inner spindle and the position of the outer spindle. And so that is what we can do here in sequence number 5. We can take those known values of the upper, lower, and the ball joint and the outer tie rod, and we know the distance from each of those points to the inner spindle, because those are direct measurements that we took from, again, the spindle in our bench measurements, and we can calculate that point. And then for the outer spindle, we do that same calculation again, except instead of using the distances to the inner spindle, we use the distances to the outer spindle. And we use that trilateration function to calculate the position of the outer spindle. So now we know all of the points of our spindle. And then one other thing we can do is if we know the distance from the spindle to the tire contact patch, we can actually calculate where that center point of our contact patch is. Now, that's a little rough measurement because obviously we've got tire deflections and things of that nature, but we can get kind of a rough idea. But and that's what we do here in sequence number 7 is we're trying to calculate the center of the tire contact patch. And so that is another measurement you would have to have as an input, is the distance from the inner spindle and the outer spindle to the contact patch, and then plus the distance from the center contact patch to the outer tie rod. And so that just gives you kind of a rough idea where that center point of that contact patch is. Okay, so now that we've got our system created that's going to calculate our front position of our suspension system, let's go test our results and see how well this thing works. So I'm going to come over here in the console and I'll clear out my original console values. And let's go look at what I currently have as an input. So right now I have, for the right front suspension, I have the input for the shock length to be 17 inches. So now one thing to note in this code that I wrote here, I only did this for the right front suspension, and I did that just to simplify things for this video. If you wanted to do this for the left front suspension, you could do that equally as well. One thing you'll notice in this code, I had a lot of these set up as two-dimensional arrays in Python, and so I had the first position as the left side of the chassis, and the second position, or position 1, column 1, being the right side. So that is something you can do in your code. You know, just get creative, do it however you want. So anyway, let's take a look at this and see. I've got the right shock length at 17 inches, and then I've got some other just tire parameters for contact patch calculations. I was playing around with some different stuff, trying to incorporate some tire deflection, but that's neither here nor there. So if we come back over here and we look at this model in our inventor model, I have the let me find it here, right front shock at 17 inches. So right now both of these models should be identical. So if I run this here, I get some results, and let's just go take a look at this for. So if I look at our results here, I'm showing a right front shock length. The X coordinate is 50 inches and 882 thousandths and some change. So let me come back over here and we will measure the lower shock position, and it is 50.882, which is correct. Our Y position is minus 24.687. Come back over here, minus 24.687. So the lower shock calculation was correct. Let's go look at one that was later on in the sequence. Let's look at the outer tie rod. So outer tie rod, the Y dimension is minus 26. Let's see, minus 26.667. So let's come over here. Minus 26. If we look, come over here. Minus 26.668. So our Python code's actually taking it out to further decimal places. So, okay, so the next part of our test here will be to change the shock length. So let me come over here and I will change the shock length to be what, 18 inches, let's just say. So there we just saw this suspension moved, and I will come over here and change this shock length to be 18 inches. Oop. And then I will, let me come over here, I'll clear this console, run it again. Okay, so I've changed the shock length to 18 inches. Let's run this again. Okay, so now I've got new values. So let's come back over to our model. Let's remeasure. Look at that outer tie rod again, and it is now minus 26.994. Come back over here, minus 26.994. Okay. Now let's try just going the other direction. Let's set that to 16. So let's go back and we'll change that shock length to 16 inches. And let's see what we get. Let me come back over to our come back over here to our Python code, and I will change that input to be 16 inches. Okay. So now we've got a new value for our Python code of minus 26.274. Okay, let's come back over to our solid model and we'll measure the new position of the outer tie rod. Minus 26.276. Come back over here. We were at minus 26.275. So a little bit of variance there. A thousandth of an inch. Maybe less than that. Let's try and see what our lower shock mount was. Minus 24.530. Let's go see what our lower shock mount was with the 16-inch shock. So right there, minus 24.530. Let's come back over here, lower shock, minus 24.530. So pretty accurate. And so there you have it. There is how we use trilateration to step through a sequence of calculations to calculate all of the points, unknown points of our front suspension. And so what you can do is you can use this to, again, all of those spindle positions. You can now calculate your camber, your caster, your toe, all of that stuff. And another great thing you can do with this type of calculation is you can run those inputs through a range and plot. Now you can plot your camber curve, you can plot your caster curve. If you wanted to move the tie rod in and out at different positions and see how that curve changes, you could actually run your suspension up and down and see how much bump steer you have. Now again, none of this really replaces real world measurements. I mean, I would never use this and just set a car up and go race. I mean, obviously you need to measure in the shop, but what you can do with a tool like this is you can get your car really, really close and then go do physical measurements. So that is a good part of using this. And again, another really good application I talked about before is if you have data acquisition that you've measured and you want to know what is your caster camber, what's your toe at different parts of a racetrack. Well, now if you've got a data acquisition and you're measuring all of these inputs, and let's say your DAC system has a GPS on it, you now know where your car is on the track and you know what the suspension is doing at that particular time. Well, now with this type of calculation, you not only know what the shock travel was, but you can also know what all of these other calculated parameters were at a different part of the racetrack. So that is how we would go about doing the calculation using a GPS style of calculation. So I'm going to do a second video where we don't use the GPS method. It's going to be the same general approach, but we're going to use some numerical methods, using Newtonian methods. And so be looking out for that video. And then I'm also going to do a third video where we do this same type of calculation, but for the rear suspension of a dirt late model. So if you're not familiar with a dirt late model, it's a pretty complex mechanical system. It's got bird cages. The axle is actually decoupled from the suspension links. And so that'll be a pretty interesting one to do. So anyway, I hope you like this video. If it helped you out and you found it interesting, again, please help me out. Subscribe to my channel. It's free. Doesn't cost you anything. Like the video. And any questions or comments, by all means, let me know. And if you would like to see maybe a deeper dive into the trilateration calculation, I can do that. Or if you want to see, cross product, dot product functions that you might have to use in Excel, let me know. I could always do videos on those type of things as well. So anyway, I hope you liked it, and thank you for your time, and till the next one. Thanks.